In this video, we will be talking about the system operation. So let's try to see how things get started in a computer and how does the operating system load up. So the operating system starts up with the Bootstrap program, and this Bootstrap program is essentially stored. It is residing in the ROM, which is a non-volatile memory. So even the non-volatile memory. So even if the power goes off, the contents of that ROM remain there. Or it could be in the electrical EEPROM. So electrical erasable programmable ROM, which is also non-volatile. So the Bootstrap program resides there, which is also called as the firmware. So this is sort of the bare bones of kicking things off. It is not the operating system, it is the things that bring the operating system into the memory and start its functioning. So the operating starts with this Bootstrap program, and once that firmware is loaded onto the memory, it is going to, from then on, it is just going to wait for events. And events are usually interrupts. And interrupts can be further classified as either coming from software, so software interrupts, or they could be from hardware, for hardware interrupt. So software interrupts, usually called as traps or exceptions. They could be several different types of software interrupts. So for example, it could be a system call. It could be an error, for example, divide by zero error, or a memory violation. So any of these errors, if they occur, they would be classified as a software interrupt, and the operating system would have to wait until any of these interrupt situation happens to be able to respond to that. Next, the hardware interrupt is going to be initiated because of a I/O device trying to interrupt the CPU, and it's trying to gain the CPU's attention. So that is, for example, to complete an I/O operation. So that's called a hardware interrupt. So those two types of interrupts are going to, the operating system is going to wait for those interrupts to happen. Um, let's see. How do we handle those interrupts? So if we look at one of any of those interrupts, the first thing the operating system needs to do is to be able to save all the registers, various flag registers, the state of the machine, and the instruction at which it is currently going through a process. So right now, whatever the instruction is being executed, it is going to save the instruction, it is going to save the state of the machine. Next, it's going to disable any further incoming interrupts so that the current interrupt can be handled, and it is going to transfer control to an interrupt service routine, which is a set of memory addresses in memory, which detail instructions as to how to respond to that particular interrupt. So ISR, or interrupt service routine, is going to be per device. So usually it is device specific, and this is how the operating system responds to that particular interrupt. And ISRs are, again, these are a vector of addresses in memory. So we have saved the state, we have disabled new interrupts, we have transferred the control to ISR, we run through all the instructions that are in the ISR for that particular interrupt, and then after we get done with interrupt service routine for that particular interrupt, we restore the CPU state and bring that interrupt in the instruction address that was interrupted back into the program counter, so that we can resume the operation of that particular process that we were currently executing when all of this started. An operating system is mostly interrupt driven. So until an interrupt happens, it is just going to wait for some event to happen. So let's try to illustrate this concept of interrupt using a timing diagram. So the x-axis over here is time, and there are two things that are being monitored. There is the state of the CPU at the top, and there is the I/O device at the bottom. So the CPU state the CPU could either be executing a user process, or it could be in the middle of, or it could be servicing that I/O interrupt request. Um, the I/O device, so a certain device that is responsible for, say, a hardware interrupt, for example, a keyboard. It could either be in the idle state or in the transferring state. So things will start off, but when the I/O requests for the CPU's attention, and at that time the CPU is going to write a few registers in the I/O controller, also called as the device controller. Let me let that I/O or device controller, and that will initiate the I/O operation. So that happens at that time step. And when that happens, the control is going to be well, the transfer of data is going to happen after the CPU writes those registers, and that transfer of data is between the device and its local buffer. And then once it is done, it is going to send an interrupt to the CPU suggesting that I am done with that data transfer. So CPU services are interrupted at that place to complete that IO transfer. We will be taking a look at a little bit more detail about what happens at each step in another diagram. But right now, we know that the IO device has requested CPU's attention here. It has to write a few registers to let the device controller know what to do with that particular request. It's going to transfer some information between the local buffer and the device. Then it's going to ask for the CPU's attention to process that IO interrupt. So during that little short time, the CPU is going to be busy processing the interrupt, uh, but the rest of the time it is executing the user process. So let's take a look at the I/O structure. Each I/O device, and there could be many I/O devices that are connected to your computer. Each I/O device will have a I/O controller or a device controller. The CPU will initiate I/O by writing the specific registers in the device controller. Um, and once that is done, there could be two scenarios here. The running process, whatever process is currently being executed, can either wait for that I/O to complete. We call that synchronous I/O, which means that I will have to wait for that I/O to complete, and I cannot use the CPU to do any other thing during that time. So, which is going to make things slow. And also, the because of synchronous I/O, because we are waiting for that I/O to complete, we can have at most only one I/O at any time. So imagine your keyboard and mouse being those are both I/O devices, and if they are using the processor, it is very inefficient for only one device operation to go through. We would want multiple devices to be included in this. So the I/O completion, I/O interrupt for multiple devices being staggered or run in parallel, which cannot be done using synchronous I/O. One advantage, however, with synchronous I/O is the operating system is going to know which device has requested for that I/O, which device raised that hardware interrupt. Um, the second option could be uh, the IO request has been initiated. Once that initiation has been done, the CPU acknowledges it. However, it proceeds anyway, so it does not wait for that IO to complete, but it just goes on with its current process. So that's called asynchronous IO. In this one, more than one IO at a time can occur. But because we are not addressing or servicing that IO request, we are going to need a device status table, so something that can keep track of all the IO requests. So a typical device status table over here is shown. So for example, there are several devices, and each device and its status is listed. So for example, we could have card readers, line printer, and so on, and we can have the status showing as either busy, idle, or not functioning. And the processor is going to maintain all these requests in a table form and service them based on some sort of algorithm, or uh, based on whichever request comes first, which is handled by the operating system. And as you can see over here, there are a couple of them that are showing busy. For example, there's a line printer with a certain address, and the length of that request is provided. And note that if there are multiple requests by the same device, then they are going to be have to maintained in a queue, in a wait queue, as indicated over here. So busy, idle, or not functioning, keep the status in a device status table, and then instead of waiting for IO to complete, uh, do that. Don't stop the CPU user process, but instead maintain all of those IO requests in a table and service them separately, independent of the user process. That will speed things up, of course, so that will make it much more efficient to be able to go through the process and simultaneously service the IO requests or the hardware interrupts. So let's take a look at the synchronous and the asynchronous I/O in a little bit more detail. Over here, we are showing two block diagrams over here for synchronous and asynchronous I/O. At the top, you have the user space being listed, which is essentially a user process that is currently being executed. And that could be a synchronous I/O operating system, or it could be a synchronous asynchronous I/O. But below that user space, you have a kernel space, which includes a device driver, which is specific to that particular device, an interrupt handler, and at the bottom you have the hardware, which comprises of the IO device itself and the IO controller or the device controller, which is where the data transfer occurs. So let's see what happens at the start. So to start an IO operation, the device driver is going to load appropriate registers within the device controller. So the device driver, which sits right under that process, that is going to load appropriate registers in the device controller or hardware controller, which is way at the bottom over here. And then the device controller in return is going to examine the contents of these registers to determine what action needs to take place. The controller then starts the data transfer from the device to its local buffer. And as we discussed earlier, the device controller is comprises of two things. One is your registers and the local buffer. Once the transfer is complete, and as you can see, this is the time axis, so the time, and we are waiting in the case of synchronous IO for that transfer to get completed, so it's going to take some time. Once the transfer is complete, the device controller will inform the device driver via the interrupt that it has finished its operation, and then the device driver then returns the control to the operating system, which can go back to executing the user process where it left off. So it will pick it up where it stopped. Now the key difference between synchronous and asynchronous is that that particular loop that happens for each process, each IO interrupt, is spreading things out in time because we are waiting for it. But instead in asynchronous, that complete cycle happens for and several of these could happen in that same amount of time. So that's the key difference, which increases your system efficiency. But those are the same steps involved. You return to the process immediately, after writing the register. So the first few steps are the same. So you still use the device driver to load the registers, and then the device controller will examine those registers to take care of the data transfer later. So it writes the registers, and then it comes back to the device driver, and the control is given back to the process. So we are not waiting over here, which makes the efficient use of time and resources. Okay, so this is a quick discussion on system behavior and how interrupts work and how synchronous I/O is different from asynchronous I/O. Some advantages and disadvantages. The next thing that we have is to talk about the hardware protection. So we'll do that in the next video.